Okay, let's dive right into this explainer with a pretty massive fundamental question about facility emissions. How can regulators possibly know a plant is accurately keeping its invisible carbon monoxide levels low? I mean, think about it. We are talking about a gas you can't see, you definitely can't smell, and yet it is strictly monitored to protect the environment and public health. So, how on earth do we trust the machines doing the measuring?
Well, the answer lies in a dense regulatory document called Performance Specification 4A. This specification acts as the ultimate test to ensure monitoring equipment is actually telling the absolute truth right at the time of installation. It is essentially the rulebook, the gold standard that guarantees a facility's monitoring hardware isn't just plugged in, but is actually highly accurate and legally compliant from literally day one.
Here is exactly how we're going to break down the anatomy of this standard today. 1. Decoding specification 4A. 2. Safety and gear requirements. 3. The big three metrics. And 4. Alternative compliance procedures.
Let's start with Section 1, Decoding Specification 4A. To really understand this document, we first have to define CMS. That stands for Continuous Emission Monitoring Systems. You can kind of think of a CMS as essentially the facility's speedometer for tracking pollutants. Just like you wouldn't trust a car whose speedometer hasn't been calibrated, right? Well, regulators won't trust a facility's emission reports unless the CMS has been rigorously tested. Now, there's a really interesting caveat here. PS4A isn't driving the car. It's simply the initial test applied at installation, specifically for facilities with low emission standards, those regulated at less than 200 parts per million by volume. And notice a key detail. This specification is explicitly not designed to evaluate the CMS performance over an extended period of time. It's just the initial hurdle. Furthermore, it doesn't even tell operators exactly how to calibrate their specific machines. It just demands that the final results are accurate. The burden of figuring out that calibration, that is entirely on the source owner. Moving right along to Section 2, Safety and Gear Requirements.
Before anyone even thinks about touching a dial, the specification clearly mandates that operators establish strict health practices. Why? Because these tests actively involved hazardous gases. The document flat out states that it doesn't address all the safety problems associated with its use. If you are the user conducting these tests, you are fully responsible for checking the manual, figuring out the regulatory limitations, and making absolutely sure your team is protected from the hazardous materials you're working with. No short acts. Once safety is totally locked down, we get into the physical gear, specifically the data recorder scales. To catch both normal conditions and sudden short-duration spikes without any kind of concentration gap, dual-range capabilities are required. You have very strict mathematical parameters for setting your low and high-range scales. For your low-range scale, the high-level value has to be set between 1.5 times the emission standard and the span value. But for your high-range scale, you have to set a high-level value at a minimum of 2,000 ppm. This dual-range system, which can be two separate analyzers or just one dual-range unit that switches automatically, ensures you literally never lose track of carbon monoxide levels, whether they're at a steady hum or suddenly spike way off the normal charts. However, if your facility maintains consistently low emissions, the rules actually provide a bit of flexibility. A single-range analyzer is allowed, provided that normal and spike emissions can be quantified. In this case, the operator simply sets an appropriate high-level value to include all expected emissions. So the regulation is incredibly strict, but it adapts to the reality of a consistently clean operation. Real quick, before we dive into the heavy math and testing procedures of the next section, take just a second to subscribe to the channel. We absolutely love taking these incredibly dense, heavily technical regulatory documents and translating them into clear, structured explainers just like this. If you are finding this breakdown helpful, hitting that subscribe button ensures we can keep demystifying complex environmental regulations for you. All right, let's get into Section 3, the big three metrics. So your system must pass strict limits for calibration drift, relative accuracy, and hit a snappy response time of under 1.5 minutes. Let's look at these individually. First, for calibration drift, the machine cannot deviate from the true value of your calibration gas by more than 5% of the span value for 6 out of 7 test days. That proves the system is stable. Then you have relative accuracy, or RA. The RA must be no greater than 10% when using the average reference method value, 5% when using the emission standard, or simply within 5 parts per million by volume. And finally, the response time.
When gas actually hits the sensor, it cannot take longer than 1.5 minutes to register 95% of the final stable value.
So to actually measure that 1.5-minute response time, operators must perform this precise 3-step procedure, and they have to do it 3 separate times. First, you introduce a zero gas into the analyzer and wait until the output stabilizes, meaning no change greater than 1% of full scale for 30 seconds. Next, you introduce an upscale calibration gas and start the clock. You record the exact time it takes to reach 95% of the final stable value. That is your upscale response time. Finally, you reintroduce the zero gas, wait for a stable reading all over again, and record your downscale response time.
Keep in mind, though, that your official system response time isn't just your best run. You run that entire cycle 3 times to get your mean, or average, upscale and downscale times. The official system response time is strictly determined by whichever average is slower. The regulators honestly don't care how fast your system reacts at its best. They care about how slow it reacts at its absolute worst. It's basically a built-in safety net to ensure no sudden carbon monoxide spikes are ever missed.
Which brings us to Section 4, Alternative Compliance Procedures. What happens if your facility is just crushing it? If your average carbon monoxide emissions are verified by reference method 10 to be less than 10% of the regulatory standard, you actually qualify for an alternative approach. This is essentially a reward for operating a highly efficient, very low-emission facility. And this brilliantly illustrates the regulator's flexibility. Instead of a full, rigorous relative accuracy test, you can perform what's called a cylinder gas audit. But there's a very specific catch here. Your cylinder gas used for this audit must contain carbon monoxide and 12% carbon dioxide. Why that exact mix? Because it acts as a vital interference check. The continuous emission monitoring system has to prove that it is entirely free from the effects of interferences from other gases, like CO2. So even when the rules are relaxed for clean facilities, the science required to prove that cleanliness remains incredibly precise. Finally, while Performance Specification 4A sets a rigorous initial baseline to ensure these tools are completely accurate, it leaves us with a pretty provocative thought. As we discussed earlier, this specification is entirely about the time of installation. The source owner is legally responsible for calibrating and maintaining that accuracy moving forward. So if PS4A just proves the system works on day 1, who makes sure the system stays accurate years after the initial test is actually done? It's a huge question of long-term accountability in environmental protection that goes far, far beyond the initial installation. Thank you so much for joining me on this explainer, and I'll catch you next time.